Ampere's law is one of the big ones. Okay, this is one of those things you've got to understand. In electromagnetism, we have these 4 laws. One of them is Gauss's law, and now we're doing Ampere's law. And then we're going to do, there's a couple more after this that make up the 4 laws that are called Maxwell's equations. And so now, before we get to Ampere's law, I want to remind you of, do a little bit of review for electric fields. And remember with electric fields, to figure out what electric fields were, well, at first we could use, we had Coulomb's law, right? We had, okay, the electric force, well, the electric field based on Coulomb's law was equal to K, and we went dq over r squared in the r hat direction. I don't know if you remember that, but this is what we did, and it was really hard to use. Using Coulomb's law to figure out electric fields is a pain in the neck. And so what we eventually did is we used this for a point charge. If you recall, we chose a point charge, and we said we surrounded it with a surface area. And from that, we developed Gauss's law. And what we found was that, we got Gauss's law, and what Gauss's law was if you had a really symmetric charge distribution, it was a way of figuring out what the electric field was very easily, way easier than using Coulomb's law to figure out electric fields. This was almost impossible, but this was pretty doable as long as you picked a Gaussian surface, an area that matched the symmetry of the electric field, and you figured how much. It only depended on how much charge was inside, and you could solve for the electric field. Very, very nice. Okay, now we've got the same kind of situation going on with magnetic fields. With magnetic fields, well, we've got this crazy law to figure out the magnetic field, right? B equals mu naught I over, was it 4 pi times the integral of ds cross r hat over r squared. I felt like is that it? Yeah, that's good. Okay. So this is the Biot-Savart law. And yeah, you can use it, but it's really hard to use. And so what we need is a law that's kind of like Gauss's law for electric fields. We need the equivalent thing. And that equivalent thing is Ampere's law. And what it does is it allows us to figure out the magnetic field for highly symmetric current situations. If you've got a current, what causes magnetic fields? Moving charge, currents. So if you've got some distribution of current, you can use Ampere's law to figure out what kind of magnetic field that current is going to give you. Now, right now we've just dealt with current in a long straight wire, but there are lots of things you can do. You can have a whole bunch of wires all bundled together. Or you could have a flat piece of sheet metal with current flowing through it. Or you could have a tube, a hollow tube made out of metal, like a coaxial cable that can have current. We have all kinds of current distributions, and we want to know what kind of magnetic fields do these currents create in the space around them. And we need a tool that will let us to do that. So what we're going to do is, I'll just give you the law first. Okay, and the law basically says that B dot ds is equal to mu naught times the current enclosed. Now this is Ampere's law. We're going to develop it. We're going to come up with kind of a cheesy proof of it. A cheesy proof. Oh, that sounds like a... Anyway. But here, notice the similarity between Gauss's law and Ampere's law mathematically. What causes electric field? Isolated charge. And so what do? We surround that charge with some surface area in such a way that it allows us to solve for this electric field. Well, you can't surround a current with a surface area, okay? Because currents flow. I mean, if you have a current in a wire, it's got to make a complete loop. So you don't surround currents with surface areas. What you do is you surround them with loops. So let's go ahead. So this right here. Now, what is ds? ds is a little tiny displacement, right? A little tiny line. And so what we're going to do is this little tiny line is going to create a loop, a complete loop. Now, this little circle over here, this means, hey, this surface area is a closed area. And what this circle over here means is, hey, this line is a closed line. It forms a complete loop. ds is going to be a loop. They call this a Gaussian surface. We're going to call this an Amperian loop. All right, now let's show where this comes from, okay? Let's go back to what we did with long straight wires. Now, if you recall, I know it was a long time ago, what we did, we sort of proved Gauss's law using a point charge, because we already knew what the electric field was for a point charge. And then we just said, hey, it can be shown that blah, 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 it works in general. Well, that's exactly what we're going to do here for Ampere's law. We already know what the answer is that we got from, we derived this from the Biot-Savart law. Okay, we've got a current. Now let's look at a plane right here, and what I'll do to make this drawing a little better. So here's a current in a long straight wire. Now we said that this, if I grab the wire with my right hand and I curl my fingers around, this is going to create magnetic field lines like this. Okay, now this goes kind of behind it. This is in front. Okay, now here's what I'm going to do. I am going to create a well, first of all, let's talk about the direction of magnetic field lines. If I put a bunch of little compasses on here, if I put a little compass there, the compass will point in the direction of the field line. So if you put compasses on a little table and turn the current on in this wire, all the little compasses will point along the field line. So what I'm going to do is this. I'm going to take this magnetic field right here, B, and it has a direction, and I'm going to lay a displacement on top of that magnetic field line. Right on top of it. And it's going to be parallel to it. And so what I'm going to do is this. I'm going to multiply B and take the dot product with it with ds. But I'm going to make sure that ds is right on top and parallel. to it. Okay? And I'm going to, here's ds, here's ds, here's ds, here's ds again. And I'm going to sum all these ds's, and I'm just laying my little displacements on purpose. On purpose, I'm laying it on top of the magnetic field line all the way until I get back to where I started. So if I do that, if I choose to put my loop, my displacement loop, right on top of the magnetic field line, well, and I'm going to go all the way around, well, what's true about the magnetic field all the way around here? It is it's a constant, right? The magnitude of the magnetic field doesn't change. Also, B and ds are parallel to each other, and I chose to do that. So this comes out like this, and this is just ds, and I went all the way around. And the dot product goes away because I chose to make the magnetic field and the displacement vectors parallel with each other. I just traced the path of the magnetic field line. That's all I did. Well, if I do that, then this is going to be equal to, well, we know what B is equal to for a long straight wire. It's mu naught I over 2 pi, and instead of calling it A, I'm going to call it R. R is the radius from the wire out to where the magnetic field is. Okay? But here's the, now this I got from the Biot-Savart law. That this is the magnetic field. But when I sum up, now everybody look up here. When I sum all the ds's, when I go in a complete circle, what do I get? I get the circumference of a circle, which is 2 pi r. Now, something goes away here. So this is equal to mu naught times times the current in the wire. Now, look, I chose this very contrived situation that we already had an answer for. And now comes the hand-waving part. You can show that it doesn't matter what loop I surround this wire with. Remember with Gauss's law, you know, here's my charge, and it all comes out like this. And I said, this is the amount of electric flux, right? And then I said, but the amount of electric flux, I could surround it with an amoeba. And it's the same amount of electric flux coming out. Well, I can make the same argument here. If I've got this, this current, and then I take a loop, and maybe I'll start here, but I'll just go like that. So I make this crazy loop, but it's a closed loop. If I sum each little b.ds plus b.ds plus b.ds, you know, now b is getting weaker because I'm getting farther away, and b and ds are not parallel to each other anymore, so the dot product, you take the cosine theta and all that sort of thing. But if you did this, you get the same answer. It's just that this, I don't know how to do the math for this. Okay? I mean, this would be crazy hard to do. But it would give you the same answer. So this gives us Ampere's law. B dot ds is equal to mu naught times I enclosed. Now, what does this mean? Well, this closed surface, or not closed surface, closed loop integral means that, hey, I'm going to surround the current with a loop. And the product of B dot ds, when I sum all of them up, it will be equal to mu naught times the current enclosed. Now, just like in Gauss's law, when you use Ampere's law, you never have to integrate this. Why? Because I'll always choose a loop where B is constant for that loop. I'm going to match my loop to the symmetry of the magnetic field. Just as in Gauss's law, I chose an area that matched the symmetry of the electric field, such that the dot product will go away and I won't have to integrate. It'll just be the product of it. And then I can use that then, if I know how much current is enclosed by my loop, I can use, and if I know the length of my loop, I can solve for B. I can solve for the magnetic field. And that's what Ampere's law is used to do. It's used to figure out the amount, what the magnetic field is for a highly symmetric current. So we can do that now. We can do a couple of examples. And so here's an example of how you can use Ampere's law. Suppose I have a real thick wire. I mean, this baby is like pure copper, all right? And let's say that the current, so here's my example. And this just goes on forever, okay? And what I want to know is this. So here's I. Now this is, I'll give this a radius of R. And let's say the current I is evenly distributed throughout the, we've got current, the current is distributed throughout the surface area of this wire. This is what's given. So now we did have a term for current density that we used one time, a long time. It's called J. So we're going to say J, the current density, the current per cross-sectional area is a constant, is uniform. So here's what we want to find. We want to find the magnetic field for a distance away, R, where R is greater than the radius of the wire. And then for B, though, this is the killing part. What about R, B when R is less than the radius of the wire, when you're inside the wire? What's the magnetic field inside the wire? Okay, well, let's solve it. You use Ampere's law to figure it out. So for A, you go B, closed loop integral So what you do is you choose a loop that matches the symmetry. This is a long straight wire, so the magnetic fields are going to be circles. So I'm going to surround this with a circle, sort of. Now, so B is just going to be, is what I'm solving for. Now what is ds? Well, it's just a circle. So that's 2 pi r. And that's what you're going to get a lot. I mean, it's quite often it's going to be a circle. And this is going to be mu naught. Now, how much of the current is enclosed by my loop? All of it. So it's just going to be I. And so you get B is equal to mu naught I over 2 pi r. That's the magnitude of the magnetic field. Now the direction of it, you just use the right-hand rule. So it's going to be in this if I grab it with my right hand, there's the current, and I grab it, and my fingers curl around that way. So it's going to be like this, the direction of it. Okay, that was easy. And this is just the magnetic field of a long straight wire. So if you're outside this wire, it looks, even though it's got, you know, thickness to it, out here all of the current goes through, and so hey, you're good. But what about inside? What if your R is in there? Let me zoom in so you can see it. See,
you said the conductor is in magnetostatic equilibrium?
I've never said that before, no. But I suppose you could. Well, what we say is it's a steady current. Okay, for part B, oh, got to zoom out again. Okay, so we got B dot ds equals mu naught times the current enclosed. Well, this is the same. This is just B, and then ds, well, it's just a circle. It's 2 pi r. But what's the killing part? Figuring out how much current is enclosed. Just like in Gauss's law, it was figuring out how much charge was enclosed by our Gaussian surface. Now we have to figure out how much current is enclosed by our Amperian loop. So I enclosed. So let's do that real quick because I got just a few minutes left. I enclosed. Well, it depends on the how much area is enclosed by this Amperian loop. It's the ratio of the total area and the area of the loop. So it's going to be the total current times the ratio of the areas. And this is pi r squared over pi big R squared. I mean, look at I over pi r squared, that's the current density times the area of our enclosed by our Amperian loop, and that gives us and this gives us how much current is enclosed. So this cancels, and you're left with this, and so now I say B 2 pi r equals mu naught times I r squared over big R squared. Well, now we got an r that cancels here. Divide by 2 pi, so you have B is equal to mu naught I over 2 pi r squared. That's your constant stuff, and then you times r. So in other words, the magnetic field inside the wire is directly proportional to r. So if you're in the center of this wire, if you're right there, what's the magnetic field in the very center? 0. And then it gradually increases at a linear rate as you move outwards until you get to the surface. And then, well, let me rewrite this one so you can kind of see. So B is equal to mu naught I over 2 pi times 1 over r. So when you're on the outside, you have this. When you're on the inside, you have this. So if I was to draw a quick little graph, okay, and this is r, and this is the strength of the B field. You start at 0. This is the radius of your wire. You go out, it becomes this maximum, and then it goes by 1 over r, like this. So this is directly proportional to r, and this is proportional to 1 over r. Okay? And now there's a lot of examples to do. So I want you to really focus and study those examples. They're really, really important. Ampere's law is a big chunk of the E&M test. So make sure that you understand it and can use it. That is all.